This question, we have a graph, so that calls upon us to use Oizerga. Our origin here is 0, 0. The y-axis is force. X-axis is distance. Intercepts, yes, there's an intercept here, which is what we would call a F0. There is a y-intercept at F0. We can read force and distance. The gradient is delta F over delta D, which has units of newtons per meter, which is the same as spring constant, and the area is force times distance, which is the work. The area that represents the work done by the force. So there is work done by the force. There could be work done on the object, to the object, but it's the work done by the force. So the work done by the force is the area under the curve, which looks like it is S plus R. But let's investigate each of the other choices before we continue, or before we just go with D. We have A is area S minus R. So the area S minus R would be some bizarre shape like this, where we would subtract them. Can't see any meaning in that. The work we did for S and we subtract the work R over it doesn't seem to make sense. The work of just S by itself. The work just S by itself is the work done by that force above and beyond the force at a distance of 0. So that would amount to, let's say, that would be the work done on the object, or to the object. So that's reasonable. R can't be the answer, because we're looking at S plus R. R just can't be the answer because it is the work done if the force had been equal and constant throughout. So that one is out. We're left to S and S plus R. So let us try and create a situation to understand what this might be. Let's just consider a block, for example. Since we have lots of blocks on the ground in physics, let's suppose we have this block on the ground, and we're going to apply some force. Well, if we applied some force on this thing, we started pulling on it, the force would be 0. But in this case, it's not 0. In the case it's not 0 would be when there is a force of friction. So we might increase to a certain point in time, and there's no motion, there's no change in direction until the object starts to move. And once it starts to move, we cover a distance, and the force could increase and it would accelerate and so forth. But this is the case, this might be a case that would explain what this graph is really showing. Now the force, in this case, as it's dragging it, once it's in motion, is doing work against friction, and it is doing work to accelerate it. So this would represent the change in kinetic energy, and this would represent the work done against friction. So we can see what S and R, why S and R would be the work done by the force. Now the useful work would be only S. The useful work that might change the kinetic energy. Now we're not told this is the situation, but if we had applied in a situation like this, it helps us make sense of the different components to it.